In this module, we are going to continue with the similarity method solution. We did the solution for the momentum equation, looked at the special case of Blasch's solution. Now we will try to do the similarity method for the energy equation, go through the maths and finally come up with the solution for flow over a flat plate with constant wall heat flux, just like what you had for the Blasch's case. We will compare the results such that the concept of Reynolds analogy is introduced based on certain restrictive assumptions. Reynolds analogy has been already covered in an earlier module, but now you will start to see how the equations and the non-dimensional similarity equation look identical in form based on certain simplifying assumptions. So let us start with the energy equation. So energy equation for the boundary layer is given by rho Cp dt by dt plus u dt by dx plus v dt by dy is equal to k times d square t by dx squared plus d square t by dy squared plus mu phi plus u into dp infinity by dx. So this was your simplified energy equation. Now based on order of magnitude analysis and other simplifications, this term would go to 0 based on order of magnitude analysis, and also viscous dissipation term. Of the several terms that are going to be there, you would end up with only mu into du by dy whole square. So this is the only term that would be important. So this is the only leftover term. This can be given as an exercise to students to show that viscous dissipation term on simplification will give you this particular term alone. So then based on these simplifications, so we will rewrite the energy equation as rho Cp, and of course we are talking of steady state. So rho Cp u dt by dx plus v dt by dy is equal to k d squared t by dy squared plus mu into du by dy whole square. And we are talking of flat plate flow over a surface, and one of the special cases is flow over a flat plate. We do the same analysis as we did for flow over a wedge, and this is your analysis which will be simplified to flow over a flat plate. So what are the other assumptions, or what are the other considerations we have? We are going to consider viscous dissipation as being present. So this will make the analysis a little bit difficult. Viscous dissipation present. We will then make it 0 so that we will eliminate the term and see the solution. Tw of x is now a function of x. So this is a general case. This can be made to a case where Tw of x is only a constant. So we are talking of both these general cases where viscous dissipation is present and where the wall temperature is going to be a function of x. So let us define the following. Let us define Tw of x minus T infinity is equal to some g of x. Therefore dTw by dx is equal to dg by dx, because T infinity is a constant. T infinity is constant. Okay, let us define first quantity. Second quantity, let us define theta, which is a non-dimensional temperature, as T of x comma y minus T of infinity divided by T wall of x minus T of infinity, and of course my eta is equal to y u infinity by mu into x. Okay, so these definitions are going to be important for us. Okay, so Tw minus T infinity is g of x. So in case of external flow, say for flow over a flat plate, we have seen that fully developed thermally does not mean, so d theta by dx is not equal to 0. Unlike the hydrodynamics part where du by dx was equal to 0, here we are going to say that thermally fully developed means d theta by dx is basically not a function of x. So, this is actually, this would be d theta by dx fully developed thermal means it is not a function of x. This is what has been proved to us earlier. So, we will keep this in mind and let us consider the fully developed case. So, thermally fully developed also is what we are considering, thermally fully developed. Okay. Now, we have to write what is the aim of similarity method. So, you have u, v, t, all of these as functions of x comma y. Okay. Just as we did in the momentum equation, we will transform this u and v to some f, some function f, f double prime, so on and so forth, and this t is now going to be transformed in terms of the variable theta. Theta is going to be there, and all the dependent variables u, v and t are now going to be only functions of eta, the new similarity variable which is eta, and you are going to have an ordinary differential equation. This PDE will now become an ordinary differential equation with eta as the new independent variable. So, that is what is our aim. So, every term here, we have two terms on the left hand side and two terms on the right hand side. We are going to write just as we did for the momentum equation. So, we would write for u, we would write for dt by dx, v we have already found out from the momentum equations analysis, dt by dy, and of course du by dy we have to write. So, let us consider dt by dx. So, what is t? Our definition of t is this. So, t is, just let us write for the sake of completeness here, t is nothing but theta of eta into t wall of x minus t infinity plus t infinity equal to t of x comma y. So, this is just rearrangement of my definition. Now, dt by dx means I am going to differentiate this with respect to x. When I differentiate this, t infinity is a constant, so t infinity with respect to x will be gone. We have a product rule here, theta and tw. So, this will be d by d theta of dx times this bracket which is just going to come out, and then theta would come out and d by dx of this bracket. So, I will just write this is going to be theta of eta d by dx of t wall of x minus t infinity plus tw of x minus t infinity d theta by dx. Of course, dt infinity by dx is 0, so we don't write that. So, this if you recall, this is only a function of x, this is a constant. So, this being a function of x alone, this partial becomes a regular derivative. So, I will write theta of n dtw by dx plus t wall of x minus t infinity as it is, d theta by dx is going to be written as just like that. We will then transform this to the d theta by d eta times d eta by dx, d theta by d eta and d eta by dx we would write. So, dt by dx is here for us. Next, we will write dt by dy. Dt by dy is d by dy of this quantity. So, d by dy of theta eta tw of x minus t infinity plus t infinity. T infinity constant. This is function of x only. So, we the derivative of this term with respect to y is gone. This is going to be treated as a constant. Therefore, I will get tw of x minus t infinity d theta by dy. This term also as it is. So, this is my dt by dy. This is my dt by dx. Then I have on the right hand side d square t by dy square. So, I will write for d square t by dy square. Now, d square t by dy square is equal to d by dy of dt by dy. dt by dy is here, so just bring that here. So, this is d by dy of tw of x minus t infinity d theta by dy. Again, this bracket is a constant. So, this is not a function of y. So, this can come out. So, we are left with t square bracket tw of x minus t infinity, tw of x minus t infinity d squared theta by dy squared. So, this is my second derivative of temperature with respect to y. Second derivative of temperature with respect to y. So, I have got these three quantities, and then I have also have u by u infinity is f prime of eta. This was my definition. I hope you remember that. This was my definition, and this is where the momentum equation gets coupled. So, you have u dt by dx, that also is going to have f prime of eta into u infinity. So, du by dy is nothing but d by dy of u infinity f prime of eta. So, du by dy whole squared is u infinity squared d by dy of f prime of eta whole square. Nothing, I have just u infinity is a constant with respect to y. So, that comes out and I am left with this term. Again, all these are going to be written in terms of eta. So, all this later on in the next couple of steps we will write this. D by dx would convert to d by d eta by dx. D by dy would convert to d by d eta by dy. This will be done. Okay. Now, we will substitute everything into the original energy equation. U dt by dx, v dt by dy, d square t by dy square, du by dy square. So, we have to define, or we have to go back to our definitions of u and v. So, we will just write the substituted one and then substitute for u. So, this is going to be energy equation becomes u times dt by dx. So, u theta eta dtw by dx plus u tw of x minus t infinity d theta by dx, This is your first term. This is my first term. This is my u dt by dx. Then the next term is v times dt by dy, that is nothing but v times tw of x minus t infinity d theta by dy. So, this is v dt by dy. Right hand side is equal to, you get, I am going to divide by rho Cp. So, left hand side we had a rho Cp. So, we divide by rho Cp, k by rho Cp is nothing but alpha. So, alpha d square t by dy squared is now going to be is equal to alpha d square t by dy squared. This is tw of x minus t infinity d square theta by dy square plus viscous dissipation term is going to be just written as nu by Cp du by dy whole squared. So this term is your alpha d square t by dy squared. Okay, so I have just done the maths like this, and now I will group terms which look similar. So u, v, this term. So just take a look at this one and this one. So these two terms are going to be combined. So I will get tw of x minus t infinity u d theta by dx plus v d theta by dy plus this term which was left. This term which was left is nothing but u theta eta. Remember, we had the definition of dtw here. So dtw by dx is nothing but dg by dx. This is dg by dx. This is nothing but g of x. So we'll substitute that also. So u theta eta dg by dx is equal to alpha tw of x minus t infinity d squared theta by dy squared plus nu over Cp du by dy whole square. I am going through all the steps because this is slightly involved. Now divide through g of x throughout, or just call it tw minus t infinity. So appropriately we will call. So I would get u d theta by dx plus v d theta by dy. This is exactly the way your left hand side of energy equation was. U dt by dx plus v dt by dy. There is an additional term which is here. This is because of the variation in the wall temperature. So that is going to be given by u theta of eta divided by g dg by dx is equal to tw minus t infinity will get cancelled. This is also gx. So this is going to get cancelled. Alpha d squared theta by dy squared. This part also remained as it is as before. Plus nu over Cp tw of x minus t infinity. I will write it like this because it is going to help me to define something later on. When we non-dimensionalize the energy equation, we got the viscous dissipation term having an Eckert number. Eckert number was u infinity squared by 2 kinetic energy divided by Cp delta T. So we have got that Cp delta T, and then when I transform this, when I transform du by dy this way, I would have a u infinity squared that would come out. So u infinity squared by 2 is Eckert number, and that therefore you will get the Eckert number here. So that is the manipulation which we are going to do next. So now let us substitute for u infinity, substitute for u is equal to u infinity f prime of eta, and v is equal to, this is from your momentum equation scale similarity method, v is equal to minus f prime of eta n of x d eta by dx plus f of eta dn by dx. These were derived earlier and we are just using this. This was your definition, and v is this. This was derived. So now we are going to substitute these two in this equation. We are going to substitute these two in this equation, and of course use d theta by dx. Also we remember we had d eta by dx came out to be minus eta over 2x. d eta by dy came out to be u infinity by nu x under root. We will use this also. So once I substitute these things in the equation, so energy equation becomes u d theta by dx was now going to be u d theta by dx is equal to u infinity f prime of eta d theta by d eta by dx. So this is going to be u infinity f prime of eta theta prime of eta in minus eta over 2x. Correct? So this can be written as minus eta u infinity f prime of eta theta prime of eta divided by 2x. This was my first term. Second term is v d theta by dy. I substitute for v, this is minus f prime of eta n of x d eta by dx. So d eta by dx is eta over 2x with a negative sign plus f of eta dn by dx times d theta by d eta by dy. So this was my v as it is, and this was my d theta by dy. So when I write this, this is going to be exactly this quantity f prime of eta n of x minus eta over 2x plus f of eta dn by dx theta prime of eta and u infinity by nu x. U infinity by nu x. Okay, so this is going to be there. Third term is third term remains as it is, u theta eta by g dg by dx just remains as it is. Okay. Fourth term, alpha d squared theta by dy squared is alpha d by dy of d theta by d eta by dy or alpha d squared theta by d eta squared d eta by dy whole squared, which will give you alpha u infinity by nu x theta double prime of eta. Okay, this another conversion from y to eta would give you another d eta by dy. So this would give me alpha by nu. Nu over alpha is Prandtl number, we will define that later. So you get this as your first term on the right hand side. And your viscous dissipation term, the viscous dissipation term which was nu by Cp T wall of x minus T infinity du by dy whole squared. So this one, if you are going to see, this is nothing but nu over Cp T wall of x minus T infinity du by dy is u infinity comes out common, u infinity squared. I'll write it separately, that's easier. So du by dy is d by dy of u infinity f prime of eta. This is nothing but d by d eta of u infinity f prime of eta d eta by dy. This u infinity is a constant. It's going to be u infinity is only a function of x, so it comes out like this, f prime of eta d eta by dy. This is what I am going to substitute. So square is there, so I would get u infinity squared d eta by dy. So I will write this one more step. So this is u infinity d eta by dy was u infinity over nu x f double prime of eta. So this is what is getting substituted. So you substitute u infinity squared. Square of this quantity is u infinity by nu x as it is, f double prime of eta whole square. So this is my right hand side, and I will recast this. Therefore, so if I just make this come here, it is u infinity squared over Cp t wall of x minus t infinity. Nu's cancel. I am left with 1 u infinity over x f double prime of eta whole square. And if I define my Eckert number, what is my definition of Eckert number? Eckert number is EC. Local Eckert number is u infinity x squared by 2 kinetic energy divided by Cp t wall of x minus t infinity. So this is 2 times Eckert number. So this bracket ends up being 2 times local Eckert number, and therefore I would get the RHS viscous term, mu phi term will simplify to 2 times local Eckert number divided by x f double prime of eta. So f double prime of eta the whole square into u infinity, of course, into u infinity. Okay, so this is my RHS. Now my next job is to substitute for all these together, these 4 terms, I mean these 5 terms, and do some algebra so that the governing equation, which was u d theta by u dt by dx plus v dt by dy is equal to alpha d squared t by dy squared plus this one, this term. So we have now written everything in terms of theta and eta, and we have several terms now which are going to be left over. So those things will get eliminated, or they will be grouped together to form several group of terms which have to either be constant or not functions of x and y, so that similarity is satisfied. This will be done in the next module.